I'm going to go over notes 1.4. I in my class had gotten to this parallel box plot graph. So we're going to draw not just one box plot, but we're going to draw two of them together, and it's called parallel box plots. And then it's asked to compare the distribution using socks and context. So anyway, if I go back and you can plug in the data, which you might have done it in class, but you also can just use the 5-digit summary to make a box plot. Typically, you're going to have the minimum is the left whisker, Q1 is the left of the box, and then the median is the line in the middle of the box, Q3, and then the maximum. Now, down here we have an outlier. That outlier is the maximum of the beef sandwiches. There's only one outlier. So then to make this whisker, this actually isn't going to be the maximum this time. This will be the second largest number. So you would actually have to know the data points in order to graph this with the outlier here. If you only had the 5-digit summary, if I only had this 5-digit summary, then I only know I got this 43 and the 29. I don't know what the second largest number is, but we have the data and it's at 32, which you can go back and look on the table. So anyway, that's how you set up the graph. Now you'd want to do the scale first, and you have to have one consistent scale for all of them. You cannot just drop down what those numbers are and draw those. And I guarantee you that's going to happen. And it will not be accepted. Also, don't forget to label. Another nice thing is if you do the axes first, you are much more likely to remember to label the x-axis. It would be a very common mistake on the test. Okay, and then when I'm comparing this, the distribution of fat grams for McDonald's chicken and beef sandwiches are both approximately symmetric. I'll go back to that in a second. The beef sandwiches has a center at 26, which is larger than the chicken's at 19. And there is a grams over here behind the 19 and one here behind this 24. But the machine cut it off. I didn't rerun it for this. You're just going to take my word for it. There is an outlier on the beef, but there is not one for the chicken. And then the range of the beef is 34 grams larger than the chicken's of 24 grams. And again, when we're doing socks, I highly recommend you just say center and approximate the median, but call it the center, and then do the range. They always accept the range, and it's the easiest one. You can make an argument we should use the IQR here because one of them has an outlier and the other one doesn't. All right, now back to the shape. For a box plot, to do the shape, what we do is we approximate the distance from the median to the minimum. Okay, and just don't even have to count it. I mean, you could say it's 10. Okay, and then you do the same thing going this direction. If they are approximately equal, then you just say approximately symmetric. Again, this one does have the right-hand side is bigger than the left, but it's just a tool that we use. Also, typically the College Board does not worry about the shape if they give you a box plot. They don't count it wrong if you write it out. And right now, what we want you to get used to is just doing the SOX acronym for your write-up. And so we're not going to worry about, well, this time you don't have to just write it on every single one of them. It'll be much more successful. Almost personally guarantee you that as a fact. All right, so that's it for this problem. And then this is a practice problem, then again meant to do in class and using the calculator. So I went ahead and I already put in stat edit because you didn't need to watch me type in those numbers, but I put in males into L1, females into L2, and then to make the graph, I have to hit second Y equals, and I'm at the stat plot menu. And this is where we can make up to 3 plots on the same graph. Well, we're going to do 2, and I don't really recall ever doing 3, where we make you draw the graphs. But so we need to turn these on. So right now it's factory preset to off. So I need to toggle to on, and then I'm going to come down here and I'm going to pick the one that shows the outliers. So if I go over and hit enter, now you can see this one is highlighted and the other ones are not. If this box plot will disregard the outliers, it'll just use the 5-digit summary regardless of outliers. But we're going to go ahead and do with outliers so we can see if there's outliers, and just because that's what we're going to do, because I want you to get used to seeing this. Also, if you're ever given a set of data on a multiple choice question and they ask you if there's outliers, you plug it in, draw the box plot, and if there's dots, there's outliers, and if there isn't, there isn't. It's awesome. All right, now one other thing. This is stat plot 2. If I go back to stat edit, I put in data into L1 and I put data into L2. Now, when I go back to stat plot 1, just going to leave that X list alone. And actually, typically we have been. But when I go to stat plot 2, I need to change this to L2. Otherwise, it's going to just give me the same graph for the males twice. And that's obviously not what we're interested here. So to get L2, you just hit second 2. It's just that simple. After you do that a few times, you're not even going to think about it. You just plug it in. And then always zoom 9 to graph. All right, and then there's our 2 parallel box plots. Now, a couple things. One is that, see how they do this a lot. The x-axis will go through the second graph. It is not okay for you to draw that. You cannot draw the box plot through the line. As a matter of fact, if you do that on your AP exam, they're going to know that you're just a kid that plugs stuff in the calculator and has no independent thought, and they are going to be more than happy to take off big points for doing that. I might suggest they might give you no credit for the graph whatsoever if you do that. I don't remember offhand a rubric what it said, but you will absolutely not get full credit if you draw that box plot through the x-axis. Why is it on through the x-axis here? That I can't tell you. All right, one other thing that's really nice on this calculator is if I hit trace, let me get this a little bit closer. If I hit trace, you can see down here in the bottom corner, it says the minimum and it tells you the minimum. And then if I bounce back and forth, it gives me my 5-digit summary. So I don't even have to do one var stats. I can just get it right from the trace. And then if you'll notice, it's only going back and forth on the blue graph. If I push up or down, it will go to the red graph and I can do the same thing. We can also see there are no outliers present because I picked the box plot that had the little dots on it, meaning it would use the 1.5 IQR rule. Oh, that was loud. They'd use 1.5 IQR rule to determine if there's outliers, and those dots would be separate. All right, and then we get the graph. Again, you draw a consistent scale, and I would use the trace function. So on this one, it's like 22 is the lowest, and it needs to go up to 218, but it actually needs to go up to 290. So you need somewhere in the range of 20 to 300. So I picked going up by 40s. That is certainly not the only way to do it, but to me, that was what I did. But again, that needs to be a consistent scale all the way across. Don't mess with that. You can't just drop down the 5-digit summary and mark those. And don't forget to label the x-axis. All right, so the number of contacts of cell phones for males center is, and remember, we're getting context out of the way right away, so I don't have to worry about it so much. But the center for the males is lower than the females, 109.5 versus 129. The spread for the males is larger than the females, 263 versus 196. Although I'm going to change that right now to range. Obviously, I have not looked that one over. There'll be another rescan. That'll be fun. For the males, I'm sorry. So the center is smaller but less consistent. That's not really important. Just putting that in there. So the shape of the males is skewed right. The female distribution is approximately symmetric. And again, that's just an estimate. This distance is much smaller than this distance is. So definitely skewed right. And the female, you could say maybe it's slightly skewed left. Again, I would just look at that and say approximately symmetric. And I did not mention outliers. Remember, if there are no outliers, you do not need to even mention them. All right, percentiles, that's next. So percentile is the percent of data points that are below or equal to the observed value, including yourself. So if you had the second highest score out of 15, what is your percentile? So we did better than 13, plus we have ourselves. There was only one person that did better than us, so we had 14 out of 15 equals 0.933. So that's the 93rd percentile. You have to round down, okay? Because in this one, we would have round down mathematically, but regardless, you always round down. Even if it was 93.7%, we didn't do better or equal to 94%, but we did do better than equal to 93. So you're definitely going to want to round down, and percentiles need to be whole numbers. That's pretty much the only time that's going to be the case. But a percentile needs to be a whole number. If you give the answer as a percentile as a decimal, 93.3 percentile, you will receive no credit for it. And again, that's just a lack of understanding what a percentile is, and they're fully willing to give you no credit for that. All right, then we have a stem plot over here, and then we're going to use that stem plot to answer a couple questions. So right here it says find the percentile for the following teams. The Minnesota Twins won 66 games. So here's the Twins at 66. So I include the 66 because that's them, and then 1, 2, 3 teams that were below them. So we count ourselves, we count anybody we're tied with, and then we count everybody below. And so 4 out of 30 equals 0.133, the 13th percentile. The Nationals won 98 games. They are the top team. So them and everybody included below them, which is everybody, is 30 divided by 30, and that's 1.0, the 100th percentile. And by the way, they just changed that. That used to, but have not been the 100th percentile. They changed the rules, but this is what the College Board will be grading from now on in. All right, and then the Texas Rangers won 93. So I come over here, I include ourselves, anybody that we're tied with. So I include all or both of the 93s. If there's 5 of them, I'd include all 5 of them. So the 93, and I count all those teams less than, and then that's 24 that we were us or tied with us, and that ones that we did better. That's the 80th percentiles. And again, percentiles must be whole numbers. Really, the only thing about percentiles is we just forget the rules for them. The actual counting and using the calculator to do 24 divided by 30, that is not hard. I'm sorry, it's just not. But if you're like, what the heck's a percentile on the exam, then I don't like your chances of getting it right. Okay, the next thing is normal distribution and density curves. So when we do a normal distribution, we have something called the empirical rule, or the 68, 95, 99.7 rule. And that is that 68% of all observations are within 1 standard deviation of the mean, and then it gets less and less and less if it's normally distributed. And that's why we draw this bell curve. So then when we write it, we'd have, this is mu, or the mean, then you go over 1 standard deviation, that's 1/2 of the 68% that's within 1 standard deviation of the mean. And then between 1 standard deviation and 2 standard deviations, it is not as big. That's why you got this huge piece. This one is much smaller. That one's 13.5%, and then 2.35% and 0.15%. And these are percentages, by the way, but that's fine. I'm not even going to write those in there. But these are percentages. So this is actually 0.0015. So that this is less than the top 1%. This is less than the bottom 1%. Okay, and then 95% of the observations are between 2 standard deviations, which, by the way, that's how we get these numbers. So 68, it's symmetric, 34 and 34. Then it's 95 between these two, so I go 95 minus the 68, and I divide by 2, and that tells me how much is in these two, and so on. So 68, 95, 99.7, basically all of them. All right, and then we have a couple where they use the standard deviation, this rule here, and they just give us some answers. We can actually use this on the calculator if you're watching this in review or because you missed class. You could also do this on the calculator. Your numbers will be off by a little bit. These are approximations only. Okay, so the speed of the cars going by a speed trap at Main Street and Maple is approximately normal with the mean of 37 and a standard deviation of 3. So I have a little curve. The mean is the one right down the middle, that's 37. And the standard deviation is 3, so I go up by 3 or down by 3 to make each of these. Then I can say, well, in between 37 and 40 is 34% of the observations. Between 37 and 43 is 34 plus 13.5, so 47.5% are in between 37 and 43. And so on. Now this one says how many, I'm going to actually answer the questions here. What about less than 34? So here's 34, less than is to the left, so I just bang, 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 add those 3 together, and I get 16%. Okay, now, that's good enough. All right, and then the percent of speeds that are greater than 43, so here's 43, bigger than 4. There's not many of them, right? But the average is 37, and each standard deviation is only 3 miles an hour. So 43 or faster is going to be 2.35 plus 0.15, or 2.5%. And then this one, I had to change the 47 to a 46. I think yours will say 47, but we made it needed to be a 46. It's a goof on my part there. So from 31 to 46. That's 1, 2, 3, 4, 5 of those zones, and I add them all together, 97.5. And then this one says it's a 40-mile-an-hour speed limit. What percent are speeding? So then I just go to 40. Now this one, it doesn't say faster than 40, but speeding means faster than 40. You should know that. And then 13.5 plus 2.35 plus 0.15. All right, the next one says we have another speed trap problem on Interstate 17. And speed is normally distributed for all the cars with a mean of 67 and a standard deviation of 5. So draw a density curve with 3 standard deviations in both directions. That's easy. Drop the 67, plus 5, plus 5, plus 5, minus 5, minus 5, minus 5. And you get those. What percentage of cars were going faster in 72? So that's these 3 little zones right here. And this one is 13.5. These two together are 2.5. That's just easier. So 16. What percentage are between 62 and 77? 34 plus 34 plus 13.5. Now it says, what about the speeding? Speeding is 75 miles an hour. Now, when I go to 75 miles an hour, that's right here. That's not in one of these. And I can't, even though I know this piece right here has 13.5%, it's not consistent. This piece is larger than this piece is. So there's no way to use the empirical rule to figure that out. So what we have to do is we have to use the calculator, doing normal CDF. Okay, and we got a couple more normal CDF problems, and then the z-score starts on video 1.5. So if you need z-scores and further, you'll have to go to the next video for that. But we just got a couple more problems here. This video is a little bit longer than I was hoping for it to be, but it's just how it is. All right, so what do we do about the speeding problem from the last situation? So we want to know the number of people going over 75 miles an hour, and we use normal CDF on the calculator. Now to get normal CDF, we hit second vars, and we will use this a lot. We'll use actually a lot of these, but most of them are towards the end of the year. But normal CDF number 2 and inverse norm number 3 is what we need for this unit. And we'll be using both of those, but we use the normal CDF probably more than any other particular feature on the calculator. Okay, so we want faster than 75 miles an hour. So it's really 75 to infinity. Okay, but we don't have infinity. So what we're going to do for infinity is we're just going to put in a number that is just unobtainable. Okay, so if you're going from some number to infinity, just put in no car is going 10,000 miles an hour. No car is going 1,000 miles an hour. 100 wouldn't be ridiculous. Some of us have maybe traveled that fast in a car before, but not 10,000. And then you put in the mean and standard deviation for mu and sigma. Mu, even though it's a U with the flag on it, it sounds like M for mu for mean, and sigma, S, standard deviation. They're trying to help us out a little bit here for this. Then we enter, then that paste, what it does is it puts it back into the calculation screen, and then we can hit enter, and then we can get our answer. And that is the percentage of drivers if, in fact, the distribution of the cars is normally distributed. The average speed or the mean speed was 67 and the standard deviation is 5. We know that 5.5% of the cars will be speeding. And again, how fast they'll be speeding, that depends, but that's the percentage that will be going over 75 miles an hour. All right. Then we have we have one here where it says that the mean is 12 and sigma is 2. And this is just kind of like plug and chug or practice on the calculators. So second vars, normal CDF. It says what percentage of shipments will have more than 15 rotten apples? So that'll be 15 rotten apples. I'm just going to leave that 10,000. That 100 would be big enough. You just want a completely unobtainable answer because really this is supposed to be infinity. Okay, but then I need to change mu and sigma for this problem to 12 and 2. Again, they just gave it to us. These two pieces are not thinkers. They give them to you. Don't make that part harder than it needs to be. And hit enter, paste it, hit enter again, and there's my percentage. 6.7%. I just went ahead and wrote it with 4. It doesn't matter. Don't write, not a whole number decimal though. That's never a good idea. What percentage of ships has less than 13? All right, so I'm going to go normal CDF. So 13 is my upper bound this time because I want numbers less than 13. And this is a negative infinity, but also it doesn't hurt to think of it like what's the least amount of apples I could have that are rotten. I could have a perfect case of apples with not a single rotten one. That's 0. Again, negative 1,000 or negative 10,000 is a perfectly acceptable answer as well. You can see there's the decimal. Okay, when it says between two values, when I go to normal CDF, this one's actually the easiest. You just simply put the lower as the small number and the upper as the bigger. Mu and sigma are given to us. Boom, just like that. And then between 10 and 14, what the heck, let's do this one more time. 10 and 14. And there you go. That's how you plug those in the calculator. There's some practice. I know I don't really have the ability to zoom in and out back and forth, but hopefully that will help you getting the practice on the calculator. All right, now, when we do a normal CDF problem, there's actually a proper way to do the write-up, and it's a 3-step write-up. Okay, that 3-step write-up is state the distribution, do the calculations, and conclude or make a conclusion, which means a complete sentence answer with all the context. All right, so this first one, if you'll note, these look a little bit different. Get this on the screen, sorry. These look different. This is what the College Board writes down as the perfect answer for state. This is accepted. And look at them. Look how much easier this one is. It's so much shorter. So the height of the trees is approximately normal with a mean of 17.5 and sigma is 2.6. We could have also just done this. N for normal, 17.5 comma 2.6. Now, if you switch the order, then you get no credit for it. So the thing about the shorthand is you have to do it correctly. All right, but it's not that big of a deal. I've never had a student that preferred this. Like, I'm 0 for 2,000, for real. Everybody likes this one better, but this would have been a perfectly acceptable state. But it's a little shorthand. It's the only time the College Board gives us a shorthand for the state step, but we do more normal distribution than everything else put together by a lot. All right, but anyway, you have to state the distribution, which really is just regurgitating the question back at us. I know it seems kind of tedious or lame, but you also get a third of your credit for just spitting back the question back at me. So you should never get a 0 on this problem, even if you totally freeze up. All right, do the calculations as our normal CDF. Okay, now the one thing is when you write this out, you may not abbreviate or shorten or anything. This needs to be the exact answer on your paper. I suppose here, if you maybe had the decimal different, I'm talking about right here. There is no variation allowed whatsoever. If you do something like NCDF, they give you no credit for this whole step. They don't care about the rest of it. They'll give you no points for the work. And again, it's one of those things where this is also kind of shorthand, but they expect precision. They expect it to be just right. Not L and U, not low up, not a down arrow and an up arrow. Lower, upper, mu sigma. But now remember when on my calculator, when I go, oops, I didn't hit second, I just hit bars. It says normal CDF right there. So normal CDF, and then it prompts us in order for what they want. There's no memory. You just have to write this down. Don't write the word paste there. But those 4 things, it's right there. So some people are like, well, that's messed up. Everything has to be just perfect. Well, I think it's messed up that you're complaining about it because it tells you what to do right there. Just do it. And then answer the question in a sentence. So about 16.8% of the trees at the park are taller than 20 feet. And again, it doesn't have to be the most perfect sentence in the world. You just need to use a complete sentence with the answer and context. And the world's in a perfect place. Also, like sometimes they might, like if I would have done it this way and didn't write feet, or on this one over here, I don't write hours, my context is picked up over here. So I got hours right here. And it's taken care of. So this actually, they require this. Plus, if we make a small mistake over here, sometimes the context will take care of that mistake for us. All right, last problem for this video. The life of a 50-hour power bank does not actually last 50 hours. The amount of time, or the amount is approximately normal with a mu of 51.1 and sigma of 1. Okay, what percentage of batteries last less than advertised? And this is actually quite a common practice. Company will make sure that the average is higher so that if anybody tests their product that it either is equal to, because some of them aren't going to last 51.1, some will be less. They even want the ones that didn't quite work out as good in manufacturing to still last as long as it's supposed to. So normally distributed, mean is 51.1, standard deviation is 1.0. Check. Normal CDF, I didn't even see. That would have not been good. That was not on purpose either. Normal CDF, lower upper mu sigma. Again, don't think about these. You're getting them right off the question. This one, you have to think about. So up here on the tree problem, it said larger than 20 feet. So 20 feet was the minimum, and then I put in 1,000. I don't think there's a tree that's I don't think even the two monster trees out in the west, or the two tallest trees on the planet, are 1,000 feet. So that is a completely unattainable value. So that's like the same thing as infinity, basically. Here, you can't have a battery pack less than 0 hours. So I just go with 0. But you can put negative 1,000 there as well, and then type it in, and about 13.6% of the 50-hour power banks will last less than the 50-hour charge, or the 50-hour advertised charged. All right, there's 1.4 notes.